mass, 0.4 kilograms, is initially moving to the right at 30 meters per second. After hitting the wall, the ball is moving to the right at 20 meters per second. What is the impulse of the net force on the ball during its collision with the wall?
All right, so because direction is important here, we need to make sure on those velocities we have our positive for meaning to the right and our negative for meaning to the left. So when we put in those velocities into our impulse momentum theorem, and we're going to use the impulse is equal to mass times change in velocity portion of that, and we end up with positive 20 kilogram meter per second. The positive just means it's to the right. Correct answer A there.
Yes, A is the correct answer. You are testing a new car using crash test dummies. Consider 2 ways to slow the car from 90 kilometers per hour to a complete stop. You let the car slam into a wall, bringing it to a sudden stop. You let the car plow into a giant tub of gelatin so that it comes to a gradual halt. In which case is there a greater impulse of the net force on the car?
All right, so both objects are experiencing the same change in velocity. They're both going from moving to stopped. They have the same mass. Because they're experiencing the same change in velocity with the same mass, they will have the same impulse. Now, what will be different, because their times are different, they're going to experience different forces, but overall the impulse will be the same. So C is the correct answer there.
Yes, impulse is the same for both of them. C. When you catch a softball, you reduce the force of impact by letting your hand move backwards during the catch. This works mainly because...
All right, when you're catching that baseball, same mass, same change in velocity. You're bringing it to a stop. By increasing the time over which you stop, by giving with it like that, you are decreasing that force. So A is the correct answer there.
Yes, A, you increase the time over which the ball slows. 2 carts, one twice as heavy as the other, are at rest on a horizontal frictionless track. A person pushes each cart with the same force for 5 seconds. If the kinetic energy of the lighter cart after the push is K, the kinetic energy of the heavier cart is...
All right, so because they have the same force for the same amount of time, they're both going to experience the same change in momentum. So if they both have the same momentum but different masses means different kinetic energies. So the one with twice the mass is going to have half the kinetic energy of the smaller one. Correct answer, D.
Yes, K divided by 2. A heavy rifle initially at rest fires a light bullet. Which of the following statements about these objects is true? There may be more than one correct answer.
All right, so number 5, third law, thinking opposite and equal forces between that gun and bullet. They're going to experience equal amounts of time for that same force. So they're going to experience equal and opposite changes in momentum. Since they both started at 0, their changes in momentum are from 0 to equal and opposite numbers, and those equal and opposite numbers will have the same magnitude, and so A is the correct answer here.
Correct, A and B, they both gain the same magnitude of momentum, and the force acting on them is the same. A small car collides head-on with a large SUV. Which of the following statements concerning the collision are correct? There may be more than one correct choice.
Okay, similar to the last one, we still have Newton's third law, so we are going to have equal and opposite forces, so A, and equal and opposite forces for equal amounts of time, equal and opposite changes in momentum, but those magnitudes of those changes in momentum will be the same, so D as well.
Yes, A and D, both vehicles are acted upon by the same magnitude average force during the collision, and both vehicles undergo the same change in magnitude of momentum. 7. 2 masses, M and 5M, are at rest on a horizontal frictionless table with a compressed spring of negligible mass between them. When the spring is released, there may be more than one correct choice.
Okay, so the spring between them, equal and opposite forces on them. So we are going to have equal and opposite forces for equal amounts of time, equal and opposite changes in momentum. Now, because they have equal and opposite changes in the magnitude of momentum, we can look and say, okay, well, if their momentums are the same, the one with the smaller mass is going to have the larger kinetic energy. Whenever we have a recoil situation like this, the smaller mass is always going to end up with a larger kinetic energy because the smaller mass always ends up with more velocity, and kinetic energy is based on speed squared. So that's why it gets more kinetic energy for the smaller mass.
A and D, yes. The two masses receive equal magnitudes of momentum, and the lighter mass gains more kinetic energy than the heavier mass. Correct. A 3-kilogram rifle fires a .005 kilogram bullet at a speed of 300 meters per second. Which force is greater in magnitude, the force that the rifle exerts on the bullet or the force that the bullet exerts on the rifle?
Third law, equal and opposite forces. C.
Yeah, that's a third law. Both experience the same force. Two objects with different masses collide and stick to each other. Compared to before the collision, the system of two objects after the collision has...
All right, so they tell us it's perfectly inelastic because they start apart and together. That means there's no change in the momentum if there's no net external forces on the outside, and we always lose kinetic energy in this type of collision.
Yes, they have the same total momentum, but they lost some kinetic energy in the process. Two objects with different masses collide and bounce off each other. Compared to before the collision, the system of two objects after the collision has...
All right, so in this case, we have them starting apart, ending apart. So that means it could be elastic or inelastic. In order to tell the difference between the two, we have to know about the change in kinetic energy. And so since we don't know about the change in kinetic energy, there's not enough information for us to decide.
Yes, that was a little tricky there because we didn't know if it was inelastic or elastic. Which of the following statements is true for an inelastic collision? There may be more than one correct choice.
So now they do tell us it's an inelastic collision, meaning that momentum is going to be conserved, so any momentum lost by one will be gained by the other, but kinetic energy is lost in this situation as well. So B and D.
Yes, B and D, momentum is conserved, kinetic energy is not conserved. That means if one loses momentum, the other one has to gain that momentum back. Which of the following statements is true for an elastic collision? There may be more than one correct choice.
Okay, so it's elastic, meaning the change in kinetic energy is zero, meaning not only are momentum and kinetic energy conserved, but if one loses momentum, the other one gains that momentum. If one loses kinetic energy, the other one gains that kinetic energy.
Yes, both momentum and kinetic energy are conserved in those elastic collisions, so any momentum lost by one is gained by the other. Any kinetic energy lost by one will be gained by the other. 13, a block A on the left has a mass 1 kilogram, block B on the right has a mass of 3 kilograms. The blocks are forced together, compressing the spring. Then the system is released from rest on a level, frictionless surface. After the collision, after the blocks are released, the kinetic energy of block A is...
All right, so this is a recoil problem, meaning the two objects push off one another, experiencing equal changes in momentum, just opposite directions. So this one will gain momentum going this way, this one will gain momentum going this way, but their momentums are the same. But if they have different masses, say one of them is a third less mass, what does that do to the kinetic energy? And we remember the smaller the mass, the larger the kinetic energy. So dividing by a third is the same as multiplying by 3. So the one with the third the mass is going to have 3 times the kinetic energy.
Yes, 3 times. The smaller mass has 3 times the kinetic energy of the larger mass. A toy cannon is fixed to a small cart and both objects move to the right with a speed v. Along a straight track, the cannon points in the direction of motion. When the cannon fires a projectile, the cart and the cannon are brought to rest. If m is the mass of the cart and the cannon combined without the projectile, and m is the mass of the projectile, what is the speed of the projectile relative to the ground immediately after being fired? And these are our choices.
All right, so we have a situation where the two objects start together, they end apart. And so I set up my equation. They are both moving together with the initial velocity v. Afterwards, the larger one, the cart with the cannon on it, comes to a stop. And we want to figure out the velocity of the projectile. So we just divide the little m over, and we get b.
Correct answer is B there. Yes, so B is the correct answer. A block A has mass 1 kilogram and block B has a mass of 3 kilograms. The blocks collide and stick together on a level, frictionless surface. After the collision, the kinetic energy of block A is?
Key word there, sticks together, meaning they will have the same speed at the end. So because they have the same speed at the end, the smaller mass will have less kinetic energy, B. Remember we talked about them having the same momentum, the smaller one is going to have more kinetic energy. Well, in this case, same speed, a little bit different.
Correct. 1/3 of that of block B. Good. An open cart is rolling to the left on a horizontal surface, rolling, so frictionless. A package slides down a chute and lands in the cart. Which quantities have the same value for the package in the cart just before and just after the package lands in the cart?
All right, the key requirement for momentum to be conserved is there's no net external forces. So it's only in the horizontal is momentum conserved, because in the vertical direction we have gravity as a net external force, meaning we'd have to include the Earth into our system of masses. So just A.
Yes, only the horizontal component of the total momentum is conserved. A yellow block and a red rod are joined together. Each object is of uniform density. The center of mass of the combined objects is at the position shown by the black X. Which has a greater mass, the yellow block or the red rod?
All right, so for center of mass, we note that the center of mass of the rod is in the center of the rod. The center of mass of the block is in the center of the block. The center of mass of the system we see is closer to the block. Whenever that is the case, the one it's closer to is the one with more mass. And so in this case, it is going to be the block with more mass.
Correct, the yellow block. 2 air hockey pucks are sliding on a frictionless surface and collide as shown in the diagram. What is the magnitude of the total momentum of the 2-puck system after the collision?
Okay, so because there's no net external forces in our system, the momentum change is 0, so the momentum before is equal to the momentum afterwards. So if I find the total momentum before, it's going to be the momentum of the first one in the I direction, the momentum of the second one in the J direction. So that's going to be the momentum at the end. So now I just need to put the I hat and the J hat together to find the total momentum at the end. So it's a 3, 4, 5 triangle. Correct answer, C.
Correct, it's 5. Yes, they don't stick together like that other Mr. Foster said, but they do have 5 before and 5 afterwards, yes. As shown below, 2 students sit at opposite ends of a boat that is initially at rest. The student in front throws a heavy ball to the student in the back. What is the motion of the ball at the time immediately after the ball is thrown and later after the ball is caught, assuming air and water friction are negligible?
All right, so since there's no net external forces, that means there's no change in the momentum. So whatever the momentum is at the start is the momentum during the throw, which is the same as the momentum after the catch. So we notice that the momentum at the start is 0 because nothing is moving initially, so the VCM is 0. The center of mass is stationary. Okay, so when we throw the ball moves backwards and the boat moves forward, but the center of mass actually stays in the same location. As soon as the ball is caught, the boat and the ball now come to a rest because both of them are moving together, and VCM has to be 0 in order for our momentum to still be 0.
Correct. The boat moves forward as the ball is thrown, and then the boat does not move after the ball is caught. Number 20, the sum of all the external forces on a system of particles is 0. Which of the following must be true of the system?
All right, so the key here is there's no net external forces. That is hinting that the change in momentum is 0, so the only thing conserved is linear momentum. So why is total mechanical energy not conserved? Take the example where I have 2 objects moving toward each other. They have kinetic energy, they slam into each other and stick, and now they have lost some of that kinetic energy. Take the example of the Earth and the ball. I throw them apart and they come back together. During that entire time, they are experiencing a force between them, but the potential energy of the ball-Earth system is changing. The total kinetic energy is constant. Nope, think about that example. 2 objects coming toward each other collide, kinetic energy drops. And then static equilibrium, no, they can be moving. They don't have to be stationary in order for this to happen. There you go.
Correct. The answer is D. The total linear momentum is constant. That's the only must.